So in this example, we're given a mechanical assembly where we have four applied loads. We have a 750 Newton load, we have a 500 Newton load, a 200 Newton load, and two 200 Newton loads. So we have, I'm going to label these as force A, force C, force D, and force E. Alright. So what we're looking for is we want to determine what is our resultant force. So we want to find our resultant force, and we want to determine our resultant moment about point O. Okay. So first things first, we're going to draw our free body diagram. So we'll have point O here. We'll have 1.25 meters separating the 750 Newton load at point A. Then at another 1.25 meters over, we'll have a 500 Newton load. That's force C, and that's going to be at an angle that's proportional to a 3, 4, 5 triangle. Alright, and then our last two forces are going to be 200 Newton forces at points D and points E. So once we have our free body diagram drawn, the next step we're going to do is we're going to find our resultant force. So we're going to find R. So R is going to be equal to the sum of all of our forces. So we're first going to define all of our forces in Cartesian form. F of A is going to be equal to 0 in the x direction and minus 750 newtons in the y direction. F of B is going to be equal to, or F of C is going to be equal to 3/5 times 500 newtons in the x direction plus 4/5 times 500 newtons in the y direction. And then F of D is equal to minus 200 newtons in the x direction, and it's going to be equal to 0 newtons in the y direction. And then F of E is equal to 200 newtons in the x direction, and it's equal to 0 newtons in the y direction. So if we add these all up, our resultant force is going to give us the 200 newtons cancel, so we end up with a resultant force of 300 newtons I, and then our y component is going to be equal to minus 350 newtons J. Alright, so that's our first value that we were looking for. Alright, the second thing we were looking for was our resultant moment about point O, and we know that's going to be equal to the sum of all of our moments applied to our system about point O plus the sum of any couple moments that are applied to our system. So first we're going to find, so since this is a 2D problem, we can use scalar moment analysis. So all of our moments will be going to be about the z will be about the z-axis. All right, you could use vector analysis, but it'll make it a little bit more difficult. So so we're going to first find our moments. So we're going to say our moment about the origin is going to be equal to the moment due to force A plus the moment due to force C plus plus the moment due to our couple, which is forces D and E. So let's calculate each of these one by one. Moment due to force A would be equal to 750 newtons times 1.25 meters. All right, and then if we use the right hand rule, our force is going down, and our moment arm is going to the right. So this would create a clockwise rotation about 0.0. So it's going to be a negative moment. Okay. So MFC, the moment caused by force C, that's going to be equal to the contributions of the y component of our of the 500 Newton force. So it's going to be equal to 4/5 times 500 newtons times the length of 2.5 meters. All right, and if we look at that component, that would be that would cause a clockwise counterclockwise rotation about 0.0, so that should be a positive moment. And then we have to add the contribution of the horizontal component of the 500 Newton force. So about 0.0, and that's going to cause a clockwise rotation, so that should be negative. So we'll be multiplied this by 3/5 times 500 newtons times 1 meter. Okay, so if we add that all together, we end up getting 400 times 2.5, which is 1,000 Newton meters, minus 300 Newton meters. So that's equal to 700 Newton meters. Okay. And then for M, the couple moment, our couple has a 200 Newton force on each side, and they're separated by 1 meter. So that's just going to be equal to force times distance. So this just to be equal to 200 newtons times 1 meter. And if we use the right hand rule, this is going to cause a counterclockwise rotation, and it's going to be equal to 200 Newton meters. Okay, so if we add this all together, what we end up getting is our resultant moment is going to be equal to minus 937.5 Newton meters plus 700 Newton meters plus 200 Newton meters, which we end up getting just negative 37.5 Newton meters for our resultant moment. So just to recap what we did in the problem, first thing we did was we drew our free body diagram to identify all the forces and all the moment arms that we would need to use to properly apply our resultant force equation, which was our second step, step 2. So once we had a resultant force equation, we then broke all of our forces down into Cartesian form. Okay, and once we had everything in Cartesian form, we could then just add them all up to find our resultant force. And then after we found our resultant force, we found our resultant moment using this equation here. And then since it's a 2D problem, we can use scalar moment equations and the right-hand rule to determine the directions of all of our moments. So, we had all of these. We solve for each of the individual moments in our couple moment, and then we add them together to determine our resultant moment. Right. And that concludes how you can simplify a system of multiple forces and couple moments to a single force and couple moment applied at a point.